Okay, any questions about friction force before we continue? What is equal to μs? Tangent theta, okay. So we have this inclined plane. This is the angle. So tangent theta is equal to μs. Okay, we have this object. We give it an initial velocity in the upward direction. Okay, so now let's first draw the free body diagram. In this case, we have this mass over here. What are the forces acting on my mass? Initially, it is moving upward. What are the forces? I mean, at this level, the only thing you have to do is just put some arrows and name your forces. That's the only thing. You don't have to write their magnitude. You don't have to write their components. In fact, you shouldn't. This is just the way the free body diagrams are, just ways for you to help you to visualize things. What are the forces? What are which arrows should I put? We have the weight, which is pointing downward. There is the normal force, that which is perpendicular to the surface, and there is also the friction force. Which way will the friction force point? Positive x, or if you still use this axis as your positive x direction, it will be pointing downhill. So this is the friction force. So the total force, the net force, will be pointing downward because the friction force is pointing downhill. The component of the weight horizontal to the incline is also pointing downhill, so they will not cancel each other, and there will be an acceleration. So it will be accelerating downhill. So you just, okay, so let's see, this is theta is equal to theta max. You push it uphill, it stops and stops. Well, it's not exactly theta equal to theta s. Okay. So you push it uphill. So you push it uphill and it comes back. And you see, ideally, what should happen is at the moment that it stops, the friction coefficient should be the static friction coefficient, and once it's the static friction coefficient, the net force is zero, so it will not accelerate downhill. That's the ideal situation. In real life, it doesn't happen. So the problem is, I mean, at least in our models, for the friction coefficient, for the friction to become static friction coefficient, it's not really enough to have zero velocity. It should be having zero velocity for some amount of time. If it has a zero velocity for a finite amount of time, then in that case it will have enough time to form these chemical bonds. It will have enough time so that the ridges, the hills, and the valleys in the surfaces will be able to go in each other. So these things require time. So if the amount of time that it has zero velocity is almost zero, then the friction coefficient will never really become the static friction coefficient. So in real life, if theta is very close to theta max, if you just push it uphill, okay. If you push it uphill, it comes down because it doesn't really stop. It stops just for an instant. And the friction coefficient doesn't change instantaneously. Any other questions? Well, in idealizations, of course, it becomes the kinetic friction, the static friction, so it should stop. But in real life, it doesn't happen that way. Other questions? Okay, so up to now we have been discussing some of the forces that we see in our everyday life. Like we talked about the weight, we talked about the normal force, we talked about the friction force, and now we will be talking about the drag force. Where do you see the drag force in everyday life? You throw a paper. It is definitely not accelerating with G. I mean, if you just throw a paper and this ball at the same time with more or less same speed, so the acceleration of this paper is much smaller than the acceleration of the ball. So now there's another force in game. Well, there are no surfaces in contact, so we cannot really talk about the static friction, kinetic friction, or the rolling friction. And this new kind of friction is what we call this drag force. It's a kind of friction force. Well, the more correct terminology is it's a dissipative force. Now the drag force is a friction force acting on solid objects, acting on objects moving in gases and liquids.
How can we find a surface? For example, when we throw a paper, you said there is no surface. Yeah, I agree with that.
What do you mean there is no surface?
For friction, this is not like this is a surface, the table is surface.
Okay.
Definitely. And there is another surface, argo.
Okay.
When we throw air at paper, it has a drag force.
Okay.
But there is no surface, we can say.
Well, there are no, I mean, in the case of the other friction, like the friction on this one, we have two solid surfaces in touch. We have this solid surface, we have this other solid surface, and they are touching each other. And the friction force is due to that surfaces that touch.
Solid surface. You use the word solid surface.
It's just a solid surface. Now, if you just move your hand in air, of course your hand has a surface. Well, air, you cannot really define the surface for the air. Okay?
Just solid surface. No, there is no surface of air, but we can, for wind, when there is wind, we can talk about the surface.
No, I mean, if you are, for example, riding a car, just move your hand, put your hand out of the window, you will see that you will feel a larger force if you put your hand like this than if you put your hand like this. So that basically tells you that that is a drag force that you are feeling. So the drag force will be basically proportional to the area perpendicular to the motion of the relative motion in the wind. So that's one property of the drag force that you can experiment in everyday life.
Call some surface being solid.
I mean, mainly yes. Now the expression for the drag force Okay, the main difference between the drag force and the other kinds of friction forces is that the drag force depends on the velocity, whereas the other forces do not depend on the velocity. For example, in the case of the kinetic friction, we have seen that it only, in most cases at least, it only depends on the normal force acting between the surfaces and not on their relative speeds. But the drag force will be a velocity-dependent force. This is the main difference. Now, how does it depend on the velocity? Well, it also depends on the velocity, and we cannot really have a general expression for the drag force. But we know that from, again, everyday from experiments, we know that if V is large, then the drag force is proportional to the velocity squared. For V is smaller, the drag force will be proportional to the velocity itself. Now, it's easy to explain this large drag force and why it should be proportional to the V squared. You see, if your object is moving very fast, let's say in a gas is nothing but just a collection of atoms. So this is our gas. And we have our object, let's say, moving in this gas, V, with some velocity V. Okay, everywhere is surrounded with the gas. Now, if the velocity of our object is large, you can just ignore the velocity of the gas molecules. That will be small compared to the velocity of my object. So in a given time, delta t, my object will move this much, let's say. And this side is just v times delta t, the speed times the delta t. So my box basically collides with all the molecules within this volume. Now, what is this volume? This is A. Now, the volume of this object is the area times the height. So it's area times V times delta T. Now, the number of molecules that it hits is just the density times this number. This is the number of collisions. Now, we will be studying the collisions later on, and we will see that at every collision, the amount of force that an object feels will be proportional to the velocity. The force per collision is proportional to the velocity itself. So we have this many collisions as my object is moving. So the total force that my object feels will be proportional to the area, cross-sectional area, the density, and the velocity squared. So this is basically where the expression in your book comes from. So it's proportional to the cross-sectional area. Whether you put your hand in like this or like this makes a change in the drag force. It will be proportional to the density of the molecules, because if you are moving in a denser region, well, you can also test it. If you just move your hand in air, you will feel one drag force. Or if you just take some honey and try to move your hand in the honey, you will be feeling a different drag force. So that's the density, the dependence on the density, and the velocity squared. If you just move your hand like this, you don't even feel a drag force. But if you just take a car and move at 60 kilometers per hour, you will be feeling a huge drag force. So it's the velocity squared. And, well, the drag force is usually defined as 1/2 CA rho times V squared. This is just a convention. I mean, that 1/2, you could have as well just absorbing this coefficient C. You might not do it as you wish. That's just a conventional way of defining it. So this is just a new kind of force that we will see in our everyday life. Now let's look at an object. Let's consider two objects. This velocity is a function of time. Let's say I take two identical objects, two of them, and we go to a very high building, and one of them we just drop, and the other one we just throw down very fast. One of them we just drop over here, one of them we drop it very fast. Now what will be their behavior? This is V0, this is equal to, let's say this is V0 is equal to V1, and in this case V0 is equal to 0. Now let's just try to understand the behavior. Now we know that there are two forces acting on it. At any time, let's say they are moving with some velocity V downward. Now what are the forces acting on my object? We are drawing the free body diagram. There's a weight, and there's also the drag force. Let's just take this as our x direction. So the total force acting on my objects will be their weight, which is mg in the x direction, minus 1 over 2 c rho a v squared in the x direction. So this is my drag force. So for the object with zero velocity, the force acting on it will be in the x direction, so it will be accelerating in the x direction. Right. Now if the velocity, for the other object, if the velocity is very large, such that this term is larger than this one, the force will be in the minus x direction. If this term is larger, the force is in the minus x direction. If this term is larger, the force is in the plus x direction. You agree?
Yes.
Others? So if v is equal to 0, if total is in the plus x direction, if in fact v is larger than 2 mg divided by c rho a square root, then ft is in the minus x direction. And if v is very large, this term is very large, this term is negative. So if this term is larger than this one, the total force is in the minus x direction. So let's see what happens. This object is accelerating in the plus x direction, so at the next instant, its speed will be larger. Whereas this object, we threw it downhill. It's accelerating in the upward direction, in the minus x direction, so its speed will get smaller at the next instant. So this will be how the velocity will change at the first instance of the motion. Now let's see. The velocity of this object, initially it was 0, so the total force was just mg. Now this term is non-zero, it's becoming larger. Since this is becoming larger, the total force acting on it is becoming smaller. But if the total force is becoming smaller, it means its acceleration, its magnitude is getting smaller. So if its magnitude is getting smaller, well, it's still accelerating. This is still small, although non-zero. So it is still accelerating downhill, but with a smaller acceleration. So the velocity as a function of time will not change so fast. So it will change like this. It will change slowly. Now let's look at the other one. This is where initially the velocity was huge. So it was decelerating. Its speed was huge, so it's decelerating. But now its speed is smaller. This term was huge. Now this term is the one that is determining mainly the acceleration. This term is getting smaller, so its deceleration is also getting smaller. So it will not decelerate as fast. It will decelerate something like this. Well, let me just redraw it. Initially, it is decelerating very fast, but then it will not be decelerating so fast. Well, the velocity of the speed of this object got even larger. So this term becomes even larger. So the difference is now smaller. So the acceleration of this object got even less. It is still accelerating downhill, but the acceleration is less. So it will make such a motion. Well, the speed of this object, it's moving down, but the acceleration is still large. The speed is still large, so it is still accelerating uphill. So this term is now smaller because the speed is smaller. This term is smaller. So it's accelerating uphill, but this difference is closing down. So the magnitude of the acceleration will also get smaller. Now, if you just continue like this, what you will observe is that their speeds will basically change like this. Their speed will get closer and closer to each other. Since this is moving faster than this value, it will slow down, so this term will get smaller. But as this term gets smaller, its acceleration is being reduced, so it will approach this value slower and slower. Whereas for the other particle that we left at freely, it will accelerate, so this term will keep growing, but as this term is growing, the difference is getting smaller and smaller. So for a given change in the velocity, we need more and more time, because the acceleration will have a smaller magnitude. So eventually, they will reach, both of them will reach this value over here. Now this V term that we define as 2mg divided by c rho a, that is in this example, is what we call the terminal velocity. So if you leave an object, no matter what the initial speed is, and let it accelerate on its own under its weight, and if the only forces acting on the object is weight and the drag force, in that case, no matter what the initial speed is, they will eventually reach this value, their terminal speed. Well, that's the speed that they reach at the end of their motion. Eventually. That's what we call the terminal speed. Now, any questions? What is some coefficient that you have to measure, just like the static friction coefficient? It will be given mainly by the properties of the liquid or the gas.
So at the point of time, it will stop accelerating, right?
Yes, because at this value of V, if you put this value of V over here, the total force is 0. So this term and this term, they are equal. So that is why when they reach this value, they stop accelerating. Their speeds will not change after that. Their velocity will not change.
I think you said that if a body accelerates, let's assume the body drops down, if it accelerates, for a particular time, the difference in velocity reduces until it becomes 0, right? So that's the terminal speed.
Yeah, when they reach the terminal speed, the velocity will not change. The change in the velocity will be 0 after it reaches the terminal velocity.
When the body is accelerating, the difference in velocity for a given time.
Okay, you see, if it is accelerating, then the velocity is changing. So when it reaches the terminal velocity, basically the object is no longer accelerating. It has 0 acceleration. when it reaches the terminal speed. So the second question is the tough one, okay?
Your usage of the word weight. Well, when you say what forces are applying to this object, you say weight, but isn't weight come from some kind of scalar quantity? Like, I would say gravity is a weight.
Okay, you see, when we talk about the weight, okay, you say that, okay, somebody weighs 40 kilos. Well, first of all, it's the wrong terminology. Weight should have the units of Newton. Now, when we say the weight, it is a scalar quantity, as you said. It's the magnitude of the gravitational force acting on the object. So that's, I usually try to use the force due to the weight.
Yeah, so when you say what forces are applying to this body,
Okay.
the word weight is not as good as like the force of gravity.
Yeah, I mean, it's the same thing. The weight is the force of gravity.
Yeah, I understand that. And the second part is this, but I don't understand why we use V squared
Instead of norm. Well, experiment.
experiment.
At least for this case, we have also a theory. This model, at least, tells me that the force should be proportional to the velocity squared.
I don't understand why.
Well, there are two parameters. Velocity affects two things. I mean, when we discuss the collisions, it will be more clear that, okay, the number of collisions is per unit time is proportional to the velocity. Because if you are going faster in a given amount of time, you will make more collisions. So that is one factor affecting the force, the Dirac force. The other one is for a given collision, the amount of force that you feel will also be proportional to your velocity. So you have the number of collisions is proportional to the V. So per each collision, the force you feel is also proportional to V. So the Dirac force turns out to be V squared. That is, we have a model, we have also experimental measurements.
We said that if V is smaller, Dirac force is proportional to V. Do we have any explanation?
Do we have?
Why is that so?
If V is large, then the Dirac force is larger than the weight.
No, in previous slide.
Okay.
Second line. If V is
This one. This one.
no.
This one. Measurement. I mean, the explanation for this one, well, I would say the Dirac force, you see, the important thing about the Dirac force is not really the explicit form of the Dirac force. It can be proportional to V, it can be proportional to V squared. The important thing is that it is a force that increases with V. So if the speed gets large enough, suppose you are dropping an object, if the speed gets large enough, eventually the Dirac force will balance the weight, whatever the functional dependence is. Now, this is all important, for example, for the raindrops. I mean, raindrops are not falling fast thanks to this Dirac force. If they were falling really fast, it will be really harmful. For example, when it rains the ice, when dolu. Okay, those ice pieces, they weigh almost the same thing as a drop of water, a drop of rain. But if you go out in a rainy day without an umbrella, there is no problem. But if you go out on a day in which you have these dolu, the raining ice, then it would hurt. Yeah. It will hurt. Because the main thing is that the terminal velocity for this hail is larger than the terminal velocity for these raindrops. Any other questions?
What value of velocity is large?
A good question. It also depends on the material. Now you see, have you seen Taylor expansion? Okay.
Yes.
Okay, forget about it. And actually, the drag force will have such an we know that when speed is zero, it will be zero. So it will be some coefficient times v, some other coefficient times v squared, some other coefficient times v cubed. You can write the drag force expression like this. Now, if velocity is large, then this term will be larger than this one. Because if velocity becomes twice as large, this v squared becomes 4 times as large, whereas this one just becomes 2 times as large. Now, depending on these exact coefficients, you can determine at which value of v this term is more important than this one. At small values of v, let's say 0.1, this is 1%, this is 10%. For if v is very small, then you can just ignore this one. Well, of course, it depends on these coefficients, which value of v is small, which value of v is large, and it requires a detailed analysis of the phenomenon, which becomes really complicated. At least we have a theory, though. We somehow understand the fluids.
This sheet is affected drag force?
Yes.
So how can be shown in the formula?
The shape, I mean, it's the area. It's mainly this area over there, the effective area. For a given area, let's say, you have this area, and behind this you have this one, or you have this one. Well, it will have very small effect. Well, it is mainly due to this area. You see, here, if you move your hand like this, the area is all of this area. But if you move your hand like this, it's the area perpendicular to the motion of the wind. It is just this area over here. The area is much smaller if you hold your hand out of the window of the car like this than if you hold it like this. Now, in this orientation, the area is much larger than this orientation. Well, just take the area. The area would be this one. Well, it depends on the system, mainly relative to the motion of the molecules in the air. That would be the main criteria. No, I mean, you see, one problem, I mean, you have a point. One problem about saying that a quantity that has a dimension is large or small is you cannot really do that. For example, if you take 10 to the power minus 5 meters, well, you can say, okay, 10 to the power minus 5 is small. But 10 to the power minus 5 meters is at the same time 10 to 4 nanometers, and 10 to 4 is huge. So you cannot really talk about the dimension, the largeness or smallness of quantities that have a dimension. You have to compare them with something else having the same dimension. So a velocity, you can only say that it is larger or smaller than another velocity. A speed is larger or smaller than another speed. That is the only meaningful comparison. Or you can say that a speed over another speed can be large or small. In that case, it will be dimensionless. Now, in this problem, it will be mainly the speed of the molecules making our liquid or gas. If the velocity of my object is large compared to the velocity, speed of the molecules making my gas or liquid, or it is small, is it small? Only compared to that one. And in that case, there's no ambiguity. Nobody can say that something is large or, I mean, everybody should say that it's large or small compared to this other speed. Any last minute questions? Okay, the circular motion, we will be discussing it on Thursday. But I just want to say one thing about the circular motion, and then your assistant that will be doing your recitation hours is here. He wants to discuss about one of these recitation hours to fix a date for the recitation hour. Okay, we had already discussed circular motion. Let's say this is an object This is the trajectory of an object making circular motion. We said that, okay, let's see, at this point its velocity is pointing in that direction. What is the direction of acceleration? We already calculated it. So if you don't remember the derivation, just review the derivation we did in last week. No, not last week, but the previous week. And we had shown that this is the direction of the acceleration. Furthermore, we also determined that the magnitude of acceleration is v squared over r being the radius. So there is this acceleration. So according to Newton's second law, there should be a force acting on my object. Should be non-zero, and F should be the magnitude of the total force should be m times v squared over r. It should be pointing in the same direction as acceleration. There is no outward force acting on anything. The only acceleration is toward the center, and that is the total force should be toward the center. Furthermore, there is no force due to the velocity of my object. There is no such force due to the velocity of my object. This is basically, if you want to have an acceleration, if you want to have an object to carry out uniform circular motion, you have to be accelerating there has to be some forces accelerating the object, and the acceleration created by those forces, whatever is creating those forces, should be equal to the v squared over r. Otherwise, you will not be able to create any uniform circular motion. But there is no force due to the acceleration, there is no force due to the circular motion. There has to be some other source of the forces. Now, we will discuss it in more detail on Thursday. Okay, so any last minute questions? Not on this one. I just wanted to mention this one, but about the drag force, about the friction. Now, just stay here, your assistant. You should also talk with him to determine about your recitation hours. Okay, see you on Thursday.
Before you leave,